Thank you. Okay. I really hate to interrupt what are undoubtedly about 23 fascinating conversations, but we want to make sure we have time for our speakers and also time for lunch. And so we'd like to begin now. So please, if you're outside the room, come back in, and I'll over to Bean.
Thank you. All right. Oh, sorry. We have our first speaker of the second session, Maya Gupta. Please join. Maya is a senior staff research scientist at Google. At Google, Gupta runs a group focused on designing efficient and transparent statistical learning algorithms, which is called Glassbox. You might have heard of it. Before joining Google, Maya was associate professor at computer science electrical engineering at University of Washington. Something that I always get fascinated by whenever I read about it is Maya actually has a company that makes wooden jigsaw puzzles. It's called jigsaw puzzles. And it's called Artifact Puzzle. And actually yesterday, I think there was a new series coming out. I read about it in the blog. And this company was founded in 2009, completely coincident probably, the very year that you're tenured at UW. Probably completely coincident. Right. But without further ado, Maya Gupta.
Thanks, Bean, and thanks to the organizers. This has been a great symposium. I'm going to talk today about how we can control machine learning better, and what do we even want to do when we talk about controlling machine learning. And I want to start by, machine learning feels very, very hot, very new, very flashy, but actually the core ideas are really old. In fact, it was the 18th century French philosopher Joseph Joubert who said, what children need is not criticism so much as role models. And that's really the core idea of machine learning. It's all about the role models, or what we call training examples, that we show to the training, and we get a model that respects those examples. And so when we talk about controlling it, that's really the best way to control your machine learning is through the data, through the examples and role models that you give it. And if you give, just like parenting, as Joubert says, if we give it constructive, good role models that do important, useful things, we will get out models that hopefully do useful, important things and behave well. So this is really the best way to control your machine learning, is to choose your examples, and you will get good learning. And I think some other people will talk more about that. But what else can we do? So that's sort of the big thing we can do. What else can we do? Well, what we're working on is trying to figure out what else do we want to do, and how do we translate those goals that we as humans might have into the math and language and algorithms to actually train this stuff under the hood and to get machine learning that does what you actually want. So I'm going to talk about a few different kinds of goals. Talk first about monotonicity, and then I'll talk about a separate set of goals, churn, coverage, fairness, that we can do in a slightly different way. But really part of the question here, and what I hope to inspire you to think about, is what are your goals? What do you wish you could control machine learning to do? Let's not just say, oh, it's a black box. Let's be proactive about what we want it to do. So first I'll talk about monotonicity. So I'm going to do a very simple example. And this is a one-dimensional, one-input example. Now, a lot of machine learning systems work on 10 inputs or 1,000 inputs or even 1,000,000 or trillion inputs, but we really only need one input here to make the story work. So let's say we're trying to recommend coffee shops, and we'll look at how far are you from a different coffee shop. So maybe we've shown some users some examples, and we got this training data from Tokyo. This is just a cartoon. And in Tokyo, all the cafes are very close to users because most people can walk to a coffee shop. So we've got some various coffee shops, and we measured how happy the users were. Maybe we asked them. So this is great. This is our training data. It's looking good. And then we can fit a machine learning model. One of the oldest machine learning models is just fit a line, linear models. A linear model in 1D just looks like a line. This is all pretty good. Of course, this is a little unsatisfying. It's kind of a very simple model. And we now have lots of big data. We want to do fancy machine learning. So we'll fit a more flexible model, maybe with a deep neural network or an SVM. So this is looking good, right? This new flexible model is much more accurate if I measure it on the purple dots. It's doing a better job fitting that data. That seems good. There is this little problem with the pink line, though, right? And I might not notice it if I just looked at my aggregate accuracy on these purple dots. But it's doing this crazy thing where it thinks that faraway cafes are actually maybe pretty good, right? Because I've got a little noise there at the end, and it's going a little crazy. It's not extrapolating well. But as long as I'm in Tokyo, I'm not really going to care much that it's doing something crazy out here because I'm not going to see coffee shops out there, so everything's probably fine. Until I decide to go take my classifier or my recommendation system and use it in Montana. And in Montana, you need to drive to get some coffee, right? So all your dots now are further away. Your examples are showing up in parts of the space you didn't train on. And you're sort of experiencing what the model is extrapolating. What is it thinking in these dark corners of the space? And that's where the monotonicity problem can really hit you. So this nice flexible model that you had was doing fine in Tokyo, but now is actually doing quite badly and telling you that you should send people really far away for coffee, which is awful at 8 in the morning. So what can we do about this? We can control the machine learning, and we can say, look, we know a priori that you don't want to have to go any further than you have to go for good coffee, so let's fit a model that is monotonic. Let's fit a model that just always goes down as the cafe gets further. And when we do that, we still do a pretty good job. If we compare that to our original flexible model, we can fit it just about as accurately. But now we've made sure that we're doing something safe, well-behaved, extrapolating sanely into those far reaches of the space. And when we take that green model to Montana, it's going to behave in a much more sensible way. So this is one example of what we mean by controlling machine learning. And this is one of the ways that we found that's most useful to control machine learning, is that we can take our humans and our practitioners' intuition about their features and about the input-output relationships and impose those on the model and still get very good accuracy. So we've been working on this for a while. We have a few different papers out. You can find a couple of them in 2016. And we've now sort of upped the ante on this and made it possible to learn arbitrarily flexible models and arbitrary numbers of dimensions from arbitrary number of samples with deep lattice networks. And this will come out at NIPS 2017. And we're going to be sharing this with everyone. This will be coming soon, coming imminently, actually, to TensorFlow. I won't commit to a date, but if you watch the Google Developer blog, you should see this soon. And we'll offer this in a few different ways, some that are very easy to use, and some that are more for experimenters who want to plug and play this with other models and sort of dig into things. OK, so this issue about monotonicity kind of gets back to this idea that the best machine learning really requires you having the right examples. Can't stress enough how important it is to have these good role models for your model, and then the right kinds of flexibility. So one of the beautiful things about deep neural networks and some of the other state-of-the-art models is how flexible they are, that they can express all kinds of reality. But we don't want them to also express the noise, overfit things. We want them to express the right kinds of reality. So what else can we do to control our machine learning, and what other kinds of goals do we have? Well, as Jess was talking about earlier, the best way to figure out how to do things with practitioners is to really work next to them. We've worked very closely with Google product teams, and I can tell you, a lot of Google product engineers, their breath smells like coffee. So the goals that we see here are coming from that close relationship we've had and figuring out what those folks need. But again, we're not sure that we're getting all the goals. We think there's a lot more work to do here, and we encourage you to talk about and think about what goals you'd like. So let's talk about some of these in detail. So the first one is what we'll call a fairness goal. We might say, look, I've got this classifier, and I'm going to use it in a bunch of countries. Maybe I've got training samples from a bunch of countries, and I want to make sure that it's sort of equally accurate in India as it is on the US. And these might be different slices of data. This might be, I want it to be equally accurate for cat lovers as it is for deer lovers or dog lovers. No one loves deer. Beer lovers or vegans, et cetera. OK, so let's say this is our goal. So one thing we could do is we could mess around with the training samples and some weights and try to upweight the ones in India and downweight the ones in the US, et cetera. But that's not going to scale very well. It's going to be kind of futzy. So instead, what we want to do is just say, hey, what your machine learning should do is minimize your errors. That's what we usually do, empirical risk minimization. But let's add a constraint that specifies exactly what you want. And there'll be some parameter here that says, well, how close do these accuracies be? What kind of tolerance are you willing to accept? And then under the hood, we'll go off and optimize that. That's a constrained numerical optimization algorithm. I was told no math, so I won't tell you how we do that. But under the hood, magic happens. And the good news is you can just do this, and you can ask for this. OK, so another kind of fairness goal might be that we want to make sure that the rate of positive classifications from our classifier in India is the same as in the US. So this is kind of like saying that the number of students from Montana getting into a university and the number of students from Texas getting into university should be about the same rate or the same percentage. So it has nothing to do, we haven't looked at the students' applications yet. We don't know who's a good, bad, or student. So it's not about accuracy. It's just about the rate of what we're going to say yes to. So this is a second kind of fairness goal. And the right notion of fairness really depends on your project and what you're trying to do. And there's a lot more ideas and ways to impose fairness. And again, we can just say, hey, let's just ask them all to do this, and we'll train for that constraint. So you say what you want, you say kind of what your slackiness there is willing to be, and you can put that in. And here's an example from the literature where they were trying to make sure that the positive classification rate for men and for women was close. So this is a benchmark data set called the adult data set. This is some work comparing to Zafar et al. And our work, the Go et al. Work. What we see on the x-axis here is what's called the fairness ratio. So over on the right-hand side, if you do nothing, this classifier classifies men positively at the rate of 6 times what it classifies women. And so just as an example, how far can we push this, and how much accuracy do we give away? So there is going to be an accuracy trade-off to satisfying these fairness goals on this classifier. And the green dots show you one accuracy trade-off, and then the red and blue dots are the accuracy trade-off that we can achieve. And the difference here really is just how directly we're imposing these fairness goals. So there's been a lot of sort of indirect work on fairness, and we're like, look, just tell us what you want, and we're just going to do it. Let's just be direct and explicit about what you want and how we solve for it. Okay, so another sort of notion of fairness isn't always relative. You often maybe just want to say something absolute about what's going on a slice of your data. Hey, for example, I want to make sure that the recall in Egypt is at least 70%. And again, you can just add this as a constraint and make sure that when you train them all, it respects this. You might lose some accuracy, but you're going to respect your constraints. And then the beauty is that you can just formulate a lot of these constraints, throw them all together, and we'll try to find a model that satisfies what you want. Now, you might be asking for something impossible, right? There's no a priori reason that you could specify anything here, and it might not be possible to solve it. But to the extent that we can try to solve and train something that obeys these. Okay, so those are sort of 3 ways we think about fairness, and both at Google and externally, there's a lot of people thinking about fairness issues with machine learning, and if www.fatmail.org is an external site that I think has a lot of great resources if you want to get started to learn more. So I won't be able to talk much more about this, but just there's a lot out there. It's an exciting thing that we're trying to proactively think about. Okay, so what else can we do to control machine learning? Well, sometimes it's hard to state what you want. Sometimes it's hard to really express in language what you want. But what you can do is look at examples, because we're very good at thinking about examples. And so what we'll see sometimes is someone says, well, I've got all this data, and it's huge and it's noisy, but I hand-labeled 100 examples that really state what should be going on. And I can't really train a huge classifier from 100 examples, so I need all that noisy data. But when you train that classifier, make sure I get these examples right, because this really captures what I want this thing to do. So again, we can just throw that in as a constraint. In general, you're going to maximize or minimize your classification errors on all this noisy data, and then try to make sure we get your examples, your sort of golden set right. Another thing that people often don't think about, but it turns out to be really important, is that we often launch and iterate these models. So maybe you've got a model out there, you've been using it, you've tested it, you're comfortable with it, everything's good, and now you want to improve it. But if you just retrain, the machine learning may make all sorts of new decisions. Some of them are good, some of them are bad. Just it's going to change a lot. And you're going to have to go through all that analysis and testing and getting comfortable again with it. So instead, you can just tell us, hey, I want a new model, but it should really be mostly the same as the old model. I don't want to have to start over. So we can add in constraints like saying, hey, on this set of examples, make sure that things don't look too different than what they used to look like. I want some differences because I'm retraining. I want something that's new and hopefully better, but only make it better in some cases. I don't want to change everything. Okay, and of course we can put all this stuff together and try to find a model that behaves and obeys all of your hopes and desires from your machine learning. So you can read a little bit more about this in our NIPS 2016 paper, Satisfying Real-World Goals with Dataset Constraints, and we're working on some more paper with a little bit more depth and experiments. And we hope eventually, that we'll be open sourcing some of this so that you can do this yourself in the comfort of your own home. Okay, so those were the kind of constraints that we're thinking about and the kinds of ways that we're thinking about. Again, what do you want to do? What do you wish that you could be doing for machine learning? Please think about it. Drop me catch me later, drop me a line later. We're trying to figure this out. Okay, so I'm going to criticize our approach a little bit because it's kind of sometimes sounds like, oh yeah, that's great. Okay, so you've solved the problem. No, we haven't really completely solved the problem. There's some big caveats about what we're doing here. One is that if I want to say something like the accuracy for beer lovers needs to be the same as the accuracy for vegans, I need to know an example set of beer lovers and vegans. I need to have some labels. I can't just constrain that if I don't have any labels. But sometimes it's hard to tell, and sometimes we don't want to know what the labels are, right? We don't want to have that privacy trade-off in order to make our classifiers obey things. So one of the things that we're trying to figure out is, well, can we make these kind of fairness goals or other kind of goals work even when we don't have labels? And we've done some preliminary experiments, and it turns out the answer is messy and sometimes. There's certain kinds of fairness goals that extend pretty well. If you make the classifier fair for some people, it will be fair for others. So maybe I don't have labels for race, but I have labels for gender. If I make it more fair for gender, I'll end up having a classifier that's also more fair with respect to race. But there's other fairness goals where there will be trade-offs, and you can actually really sort of screw things up if you don't have the right labels. So this is something we're still actively working on and trying to understand how accurate those labels need to be. Another big criticism I'll have of our approach is just the fact that it sort of relies on categories and labels, right? You know, people really are very much more individuals. This is my dad. He's from India. That's my mom next to him. She's from Holland. That makes me Dutch Indian. That means that whenever I go to like these census forms, you know, what race are you? There's like desperately trying to find another box, or I have to write in other or something. Don't fit nicely. And that's my nephew Peter, who's adorable, but he's like other squared, right? He's just, there's no box for him. This isn't gonna work. And we all sort of fall through the cracks of these things. So that's part of why we're also interested in sort of more universal notions of fairness and individual notions, and how do we smear these things. But the good news is that mostly we do find that if you get things right on categories, things do sort of smear and smooth nicely between the categories. So I don't think this is perfect, but it's also not the end of the world to be using categories as proxies for the reality. Okay. There's a lot of concerns about machine learning. I'm of course very much an optimist, and I'm very excited about all the new ways we can use machine learning and we can control machine learning. I work a lot under the hood, trying to figure out how to make the machinery that can take your wishes, translate them into math. But we need a little bit more work on the steering wheel. It's not always clear where we want to go with these things and what those interfaces should look like to humans. So as we try to bring more AI to doctors and other lay professionals rather than just engineers, how do we interface that with them? How do we explain to them what they can do and what the machine learning is doing, and make sure that sort of social contract between what the data is doing and what they're doing works. So I'm very excited that there's so many designers here and people thinking hard about these kind of HCI issues. Okay, thank you.
Thank you, Maya. We have time for questions.